Hello. This short video presentation is going to introduce time derivatives of both voltage and current in RLC second order circuits. And I'm going to do it through two simple examples here. Let's see what I have. Before you start trying to find time derivatives of voltage and current in RLC circuits, there's a couple things you definitely have to understand, completely understand. And it's the comparison here between a capacitor and an inductor. Let's start by taking a look here at a capacitor on the left-hand side. Energy is stored in an electric field in a capacitor, and voltage cannot change instantaneously across its plates. So this equation right here is extremely important. You understand that if you are either going to close or open a switch at t equals 0, I don't care if you're opening a switch or you're closing a switch at t equals 0, it makes no difference. The voltage across the capacitor before you throw the switch has to equal the voltage across the capacitor at the exact instant the switch is thrown, which has to be equal to the voltage across the capacitor after you threw the switch. That's what that tells you. This equation right here deals with first order systems, so we're not going to worry about that. And here's the next thing you have to understand. Observation: in a DC steady state condition, when all short-term events called transients have settled out, capacitors look like an open circuit. So remember, capacitors look like an open circuit to DC. And then finally, this equation right here. The current to the plates of a capacitor with respect to time is equal to the capacitance times the derivative of the voltage across the plates with respect to time. Very important three concepts there. For an inductor, let's take a look at it. Energy is stored in an electromagnetic field around the coil. Current cannot change instantaneously through an inductor. So I don't care if you're opening a switch at t equals 0 or you're closing a switch at t equals 0. The current before you activate the switch has to equal the current at the exact instant you activate the switch, which has to be equal to the current after you've activated the switch. That is extremely important. This right here applies to first order systems. We're not going to worry about that. Observation: in the DC steady state, when all short-term events called transients have settled out, inductors look like a short circuit. To DC, inductors look like a short circuit. And finally, the voltage across an inductor is equal to L di dt. So you can see the parallels between the two, but you have to get this page down, completely understand what I just told you before you can look at the time derivatives of voltage and current in RLC circuits. So the first thing we're going to do is look at this problem right here. For the circuit shown in figure 1, the value of R is 2 k ohms, L is 250 millihenries, and C is equal to 10 nanofarads. The initial current in the inductor is minus 4 amperes, and you can see where that's shown in the circuit here. And the initial voltage across the capacitor is 0 volts. These initial conditions are very important when you work second order systems. So when you're working a second order system, even when you're going into trying to find out whether it's overdamped, underdamped, or critically damped, which is another video I give you, you always have to establish the initial conditions. Now, the initial conditions, either you look at the circuit and you determine them, or in this case right here, they're giving you the initial conditions. So if you take a look here, the initial condition is the voltage across the capacitor. It's a parallel circuit, it's the same voltage. The voltage across the capacitor at 0 is equal to 0 volts, given in the statement of the problem, and the current in the inductor at 0 times 0 is equal to minus 4 amperes. You always have to establish initial conditions. Either find them or they're given to you. You always have an initial condition voltage with the capacitor, and you always have the initial condition current with the inductor. They're not going to give you voltage across the inductor, and they're not going to give you current to the plates of the capacitor. It's always voltage with the capacitor, current with the inductor. What we want to do here, if you take a look, is we want to, for the circuit shown, what is the initial value of the time derivative of the voltage across the capacitor. Well, the way you establish that, you don't have to go to a characteristic equation like you would in second order systems. This is all done in the time domain here. If you take a look, by Kirchhoff's current law at this node right here, the currents are all leaving. So I would show that as a negative IC at 0 plus minus IL at 0 plus minus IR at 0 plus has to equal 0. That's just Kirchhoff's current law. Now, Kirchhoff's current law has to hold true at 0 minus, at 0, and at 0 plus. So I'm just going to multiply through by a negative 1 there, and I'm going to get a plus there, I'm going to get a plus there, and I'm going to get a plus there. Now, if you take a look, what is the current to a plate of a capacitor? Well, in this case, it's going to be C derivative of the voltage across the capacitor at 0 plus dt. What's the current at 0 plus? Well, the current can't change instantaneously. So if the initial condition told you the current at 0 is minus 4 amps, the current at 0 plus has to be minus 4 amps. And what's the current? What's the voltage across the, what's the current in the resistor? Well, if you take a look, that's plus, or that's a plus IR, 0 plus, which we just bring down, and that's equal to 0. Well, I think you could see here that this value right here is simply, using Ohm's law, is the voltage across the capacitor at 0 plus divided by the resistance value up there. Well, if you take a look, the voltage across the capacitor at 0 is 0 volts. Voltage can't change instantaneously across the capacitor, so that numerator has to be 0. So this term here all goes to 0. And you're going to get C dVc 0 plus dt is equal to 4. If you take a look at the value of C was, up the top, C is 10 nanofarads. C is 10 nanofarads. So the derivative of the voltage across the capacitor at 0 plus dt is equal to 4 over C, which is equal to 4 all over the capacitance, which we said was 10 times 10 to the minus 9th, 10 nanofarads. And that turns out to be equal to 4 times 10 to the 8th volts per second. And that's your answer for the time derivative of the voltage in that circuit with respect to time. Now, you might ask, well, what about the time derivative of the current? Well, if you take a look it's a lot simpler to find in parallel circuits. The reason is because you know that the voltage across the capacitor at 0 plus has to equal the voltage across the inductor at 0 plus. Well, why? Because it's a parallel circuit. Because that's a parallel circuit. They have to be equal. That has to be equal to L di at 0 plus dt. And all that has to equal 0. Why? Because the voltage across the capacitor at time t equals 0 was 0 volts. So the voltage across the capacitor at 0 plus has to stay at 0 volts. And you could see that the derivative of the time derivative of the current in that circuit which is the time derivative of the dt, and that's in the inductor, by the way. It's the time derivative of the current in the inductor is equal to 0 all over the inductance. Who cares what the inductance is? The numerator 0. That gives you 0 amperes per second. And there is the time derivative of the current in the inductor at 0 plus. It's 0 amps per second. So that's one problem. It shows you how to work it out. Let's do another circuit real quick. Time derivative, and we'll use this as an example here. For the circuit shown in figure 3, there's the parameters. It gives you IS, the source current is 2 amps, it gives you L, C, RS, and R1. You can see where they're positioned. After the switch has been in its initial position for a long time at t equals 0, it moves instantaneously to the left as shown in figure 3. What's the initial value of the time derivative of the capacitor voltage in the circuit? Well, we'll find both here. Just takes a minute to find both. So initial conditions are extremely important. In this case, we're not giving you the initial conditions. You have to find the initial conditions. This is where you have to realize, where are you at t equals 0 minus to establish the initial conditions? Well, you're in position A, and then you switch to position B. Okay, so you're in position A initially. So your initial conditions that you have to pull out of this circuit here, if you take a look, the current IS is 2 amps, and that capacitor looks like an open circuit to DC. So the voltage across RS is going to be the voltage across the capacitor plates. So you can see here that the initial condition VC of 0 is equal to 2 amps times a resistance of 10 ohms, which is RS. All that current is going to flow through here. And you're going to get initial condition of 20 volts for the voltage across the capacitor. You might say, well, wait, there's a resistor here. Well, there's no current flowing through it because that capacitor is an open circuit. So there's no voltage drop across it. So the voltage drop from this point to this point is the voltage across the capacitor. That's the open circuit. There's no current flowing through R2, so it doesn't add to any voltage. Now you want to take a look at the current in the inductor at 0. Well, it's in position A. It's a source-free circuit. It's an open circuit. So the current is 0 amps with the inductor. There's your initial conditions that are very important. Now, if you take a look, we're going to throw the switch, and we want to get the time derivative at that point. So what I'd do is I'd redraw the circuit real quick. I'd just get down here and I'd redraw the circuit. Looks like this. I'm going to combine those two resistors into one resistor. Bring the R2 up and add it to the R1, because you end up with a situation like that where that field's going to collapse like this. That inductor, don't forget, current's going to maintain the same current. The field's going to collapse. So in this case right here, you end up with .01 ohms. This is 5 millifarads. And this was 5 millifarads. Millihenries, 5 millihenries. I'm getting that from the statement of the problem there. So, by Kirchhoff's voltage law now around this node here with the current flowing I, I'm just going to go around the node there. And notice that we have a VL 0 plus VL is 0 plus minus VR of 0 plus minus VC of 0 plus equals 0. As we go around that loop in a clockwise direction. So I end up with the voltage across the inductor is L, dI is 0 plus dt, minus voltage across the resistor, I of 0 plus times R, minus the voltage at 0 plus. Well, the voltage at 0 is 20 volts. Voltage can't change instantaneously across the capacitor. That has to be 20. That has to equal 0. Well, if you take a look, the current at 0 plus, in that middle term there, the current at 0 plus has to be 0 amps. The inductor is going to maintain the same current through that instant of time. If the current through the inductor is, the initial condition says it's 0 amps, at 0 plus it has to be 0, so this term goes to 0. And you end up with dI at 0 plus dt is equal to 20 all over L. If you take a look at L up there, it was 5 millihenries, and you plug that in right there, you're going to get 4,000 amps per second. And there's your time derivative for your current in that circuit. But what we wanted was, I wanted to get both the current derivative and I wanted to get the voltage derivative across the capacitor. So we want derivative of VC at 0 plus dt. That's what we want to find. We want to find what that's equal to. Well, in a series circuit, pretty easy to find that. Why is it so easy to find that? Because the current in that series circuit at 0 plus, which is the current in the inductor, has to equal the current in the capacitor at 0 plus. It's a series circuit. And we know that the current in a capacitor at all instants of time is C dVC of 0 plus dt. Well, from the initial condition, we know that the current in the inductor was 0. We know that was 0. We knew this was 0. So what you're going to end up with here is dVc, time derivative of the voltage across the capacitor, dt, is equal to 0 divided by C. Well, I don't care what C is, the numerator is 0. So you get 0 volts per second. And there's your time derivative for that. I hope this video helps you out on finding the time derivatives of voltage and current in RLC circuits. Those initial conditions are very, very important. If you enjoyed my video, please subscribe to my channels. I'd really appreciate it. Best to you. And that concludes this video.